So we've seen when we've done the chain rule that we do our first kind of derivative of the outside function, and then after we did that, we multiplied by the derivative of the inside function. So if we can integrate backwards, what we're going to have to be doing here when we're reversing the chain rule is we're going to have to recognize what was the inside function and what was the inside function's derivative, and then use those ideas to work backwards to clean things up. Now, when we did some work backwards questions earlier in the year, they were really easy to see. And here's one that's identical from your notes earlier in the year. Work backwards. This is the simplest, most basic integral to do because everything works out perfect. Can you see the power rule that the 5 came out in front and you subtracted 1 from the exponent? It's so obvious because the 5 is there and the 4 is the exponent. And then the derivative of the inside is right here, right afterwards, with 6x minus 5, or 6x plus 5. So if we were working backwards, it's easy to see that we would need a 3x squared plus 5x to the 5, because this is a perfect chain rule where nothing's been simplified. But what is going to happen to us is we're going to get into some chain rules that have been somewhat simplified, and we're integrating. And it's not easy to see what the numbers were. So what we're going to do is we're going to learn a technique, integration by substitution, to help us see this. And we did the technique a little bit when we learned chain rule, but I told you it wasn't very much fun, and we won't do it very much because it's not that useful, especially when we had chain rules inside of chain rules. But the technique that we used when we were integrating this is we said, let u equal the inside function. Then y is equal to u to the 5 by just simple substitution. And the chain rule says that dy dx is equal to dy du times by du dx. And basically what this is saying is do the derivative of the outside function and multiply by the derivative of your inside function. And this is Leibniz notation for chain rule. It's in your formula booklets. So what that would mean is whenever we recognize the inside function for doing the derivative, we'd say u is equal to that. Then we would rewrite y as a function of u. When we've done this, finding dy du is looking at your function with y and u is just 5u to the 4. And finding du dx, well, we've got u as a function of x right here. The derivative of that is 6x plus 5. Using the definition of the chain rule there, we can just write out, well, therefore, dy dx is equal to dy du, which we figured out here, and we would write 5u to the 4. And du dx is right there, and we could write 6x plus 5. And now that we've found that, we can substitute 3x squared plus 5x back in for u and get the answer. Now, the reason we didn't use this a lot with the chain rule is because you guys got quite good at just going from that original question saying, I recognize there's a function inside of another function. I do the derivative of my outside function first, keep the inside the same, and then multiplied by the inside. And so you could go directly from the original question to our answer right away. And why wouldn't you want to do that? Why wouldn't I teach you that? You would be like, Mr. JR, why are you making us do all this extra work when we go to Mr. LaFrance's class and his students just do it in one step and say, see? And then if we tried to do this technique with the double chain rule, oh my goodness, we got a couple pages of substitutions. We have to introduce u and then maybe w and then v and a whole bunch of functions inside of functions. And your brain would just go poof before you would get to the final end answer and you'd run into problems. However, when we work backwards, this idea is going to be helpful for us because it's going to help break down those questions where it's hard to see. So here we have a bunch of integrals. We're going to highlight things, and this is going to be the first step in whether for you to help you recognize when you're going to use integration by substitution. So we're going to take out, if you have highlighters, I'm going to highlight in yellow and green. We're going to look for where in an integral is an original function. Basically, we're looking for that inside function and its derivative at the same time. So here in this first one, x squared minus 7 is the inside function. And its derivative is 2x. So what you're looking for is you're looking for that inside function and its derivative. So in the second one, can you see x squared minus 3x is a function inside of another function? And its derivative is listed 2x minus 3. And this is where integration gets confusing because you're integrating, which means you're working backwards, but you're looking for derivatives within it, which is working the other way. So just wrapping your head around what am I doing, an integration by substitution, you're looking for a function that's inside of another function, and then you're looking for its derivative within the same function. This one is probably the hardest one to recognize. This one's hard to recognize because this function, x cubed minus 5x, being in the bottom of a fraction, a 1 over fraction, originally would have been inside a natural log. So that's why it's the inside function. And its derivative is right there, 3x squared minus 5. So that one there, that third one, is going to be one of the hardest ones for you to see. Here we have tan x inside of sine x. And the derivative of tan is secant squared. Here we have the natural log inside, and 1 over x is the derivative of natural log. Here we have sine of x inside the function e to the x, and its derivative, cos of x. Here we have 3 e to the x inside of cos of x, and its derivative, 3 e to the x. And this last one is going to be an interesting one to do. Because here we have sine 2x as a function, and its derivative is cos 2x. But we could have taken these highlighters and switched them up and said, well, maybe the original function was cos of 2x because the derivative of cos 2x is sine. So it doesn't matter which one we switch things around, although there will be negatives involved in some cases and not in the other. So if the original was, if the original was cos, the derivative would be sine, and the negative would be there. But if the original was sine, the derivative would be cos, and there would be no negative. So we're going to look at that and how these functions work. So we have time to do one example of our chain rule. And this is what's going to happen with the substitution. And again, I'm going to highlight things here to make it easier to see. We're going to look for an integral where there's a function inside of another function. And we're going to look for its derivative. Then what we're allowed to do is we introduce a new function u. We make it equal to our original function. So what we have is, instead of having f of g of x, we have just f of u now. But instead of having to integrate with respect to x, what we do with our function u is we say, if I take the derivative du dx of g of x, I'm going to get g prime of x. And if I rewrite that, and this is where we kind of do an interesting algebra thing with derivatives. Du dx is a derivative. But if I want to go back and integrate, if I multiply both sides of this equation by dx, I move that dx to the other side there. And then what that allows me to do is, I've highlighted g prime x here. I'm going to also highlight the dx there. And now I can replace that g prime dx with du. And so what I'm trying to do is I'm trying to change my complicated integral into a more simple integral. And if I change that more complicated integral into a more simple integral, I'll be able to integrate. And once I'm done integrating, I can substitute back to see what my original question should have looked like. So what does that mean for our question? So we're going to work through those examples that we've done before, but we're going to see what it looks like now with substitution. That highlighting thing is the first important part, because that highlighting thing tells us what we're going to make u equal to. We want to make u equal to the inside function so that we can find its derivative. So this one, if we remember highlighting, we remember that we highlighted this as the inside function and this as its derivative. So we're going to make u equal to x squared minus 7. Then if we found the derivative of u with respect to x, then du dx would equal 2x. That means that du is equal to 2x dx. Now we can go back to our original equation and now rewrite it. When we rewrite it, we've got u to the power 4, and instead of having to write 2x dx, we can now write du. Integrating this is a simple power rule. How do we integrate power rules? We're going to add 1 to the exponent, divide by that, plus c. Which means if we substitute back, our integral originally will be x squared minus 7 to the power 5 divided by 5 plus c. Do we have time for one more?